Today we're actually going to cover two readings number 3 and number 4 in cycling biomechanics. These papers have very different methods. The first one here, Hagberg et al., is a classic experiment on human cyclists. And the second one here, Neptune and Hall, is another computer modeling study where they used a computer model of the musculoskeletal system to simulate cycling and investigate cycling. So these studies used very different methods, but they have similar topics. They're both on pedaling rate in cycling, and they are also both trying to unearth or generally address the at least similar questions in terms of why cyclists have preferred pedaling rates, why I tend to prefer to pedal my bike at a certain rate of pedal revolutions per second or per minute, and what is it about that pedaling rate that makes me choose it versus some other mechanically feasible pedaling rate. Let's do a little bit of background on pedaling rate before proceeding. And the motivation here ties back into something that we brought up in the first section in class on running, where we noted that the speed that you're running at is the product of two other variables: your stride length, how far you go each stride, and your stride frequency, how frequently you're completing those strides. And this is, we talked about it for running, but it's also the case for basically any form of legged locomotion: walking, running, sprinting, hopping, whatever you might be doing with your legs. If you're doing a cyclical motion again and again to travel at a certain horizontal speed, the speed that you're traveling at is how far you go each stride times how frequently you're completing those strides. Okay? So if I wanted to travel at, say, any given speed when I'm running, I could travel at that speed with, in theory, lots of different combinations here of stride length and stride frequency. I could do it with real big, long, slow strides. I could do it with short, little choppy, fast strides, or something in between. Infinitely many, at least in theory, different combinations of different stride lengths and different stride frequencies that would all give me the same speed here on the left-hand side. Now, we saw in running that people tend not to take advantage of that versatility that I described there. Like when I'm out running at a certain speed, I'm not randomly varying my stride length and stride frequency, or at least between individuals as well. We don't tend to use like widely varying stride length and stride frequencies to all run at the same speed. We tend to have what's called a preferred combination of stride length and stride frequency, somewhere in the middle of the different biomechanically plausible combinations of stride length and stride frequency that I could use to travel at a certain speed. So what is it about that preferred combination? Why is it preferred? Why do I subconsciously choose it when I could choose something else? We saw in running that preferred combination is at least pretty close to the theoretically energy optimal combination of stride length and stride frequency. The stride length and stride frequency that allows me to travel at that speed with minimum effort or minimum oxygen consumption or minimum metabolic cost or minimum of some reasonable definition of the difficulty or the effort required of the movement. Okay. Now in cycling, there's a conceptually similar relationship, only it's a little bit more focused on energetics. You can see up here in the running relationship, there's no direct mention of energy exactly. In cycling, if we return to our energy model of the action here, the activity, if I want to travel, me being the bicycle plus the rider of the bicycle, which will have a combined mass of m, if I want to travel that whole mass at a certain velocity v, then I'm going to have to endow that mass, me plus the bike, with this kinetic energy here, 1/2 mv squared. Okay? Now, to initially get up to that velocity, starting from zero velocity, I'll have to do some work on my pedals to give the bike enough kinetic energy to travel at that speed. But then I'm not done, right? If I then stop pedaling when I reach that speed, I'll eventually coast to a stop. I lose all that kinetic energy. Where did it go? Well, it was sucked away by these sources of resistance here, these main sources of resistance: the air resistance, the rolling resistance between the tires and the road, and the internal friction of the parts of the bike. Okay? So this is why when you're pedaling, if you want to keep pedaling at a certain steady speed, you have to keep injecting additional power into the crank every second that you're cycling there. It's because you reach this kinetic energy here to travel at that speed, but then it's constantly being sucked away by these sources of resistance. So you have to keep putting additional energy via your crank power into the bike to overcome those sources of resistance and keep it at this velocity and this kinetic energy that you need. Okay? So the speed that you're traveling at on a bike is, I say here, strongly influenced by crank power, because it's that crank power that you're producing on the bike with your feet turning the pedals that's going to affect the kinetic energy of the bike. I say here strongly influenced rather than a more direct statement like dictates or produces the kinetic energy, because there's not like a direct, like, easily definable, predictable relationship here between crank power and velocity. Like if you just tell me the power that somebody's producing on a bike, I can't, from just that information, figure out how fast they're going on that bike. I need a host of other information related to like their mass and the air resistance and different parts on the bike and tire pressure, all sorts of different variables that influence the direct relationship between crank power and velocity. So determining velocity just from crank power, you generally can't really do that. But just broadly speaking, the faster that you want to travel on a particular bike under a particular set of circumstances, the more power you're going to have to produce on the crank to do that. Okay, so crank power here is sort of our analog in cycling for speed here in legged locomotion. Okay. Now, just like in locomotion, where I could use lots of different stride lengths and stride frequencies to go at a certain speed, in cycling, I can produce the same crank power with lots of different combinations of crank torque and crank frequency. Okay? Crank torque here, torque is like an angular force, like a rotational force. So this is just kind of broadly speaking the effort that you have to put into turning the crank. And then crank frequency here is how frequently you're turning the crank, how many cycles per unit time rotating the crank you are completing. More commonly in the parlance of cycling, you'll see crank frequency here referred to as pedaling rate. Okay. And rather than it having units of hertz, like cycles per second, like we saw in locomotion, pedaling rate will typically have units of RPMs, or rotations per minute, rather than rotations per second or cycles per second. Okay. So we could, in theory, have a certain power by producing relatively little torque at a really fast pedaling rate, or we could get that same power by producing a lot more torque at a relatively slow pedaling rate. And the rider will generally be able to affect this by changing the gears on the bike, like we demonstrated a few lectures ago. So let me give another demonstration of that, of how a rider might affect this. I'll pull up my video here in QuickTime. This takes a little bit longer to get going than the previous app I was using, but it tends to not pause in the middle of it, which is nice. Okay, so here's my bike again. And you guys can't quite see the crank. There it is. Okay, so my foot would, I'm not going to clip in here, but my foot would typically be resting on this pedal here, and I would push on that pedal to turn the crank there and produce torque about the center here, which is the source of my power that then gets translated to the kinetic energy and the forward velocity of the bike. Okay? Now, I'm actually pressing pretty hard here. This is not easy to do. Right now, I have my bike in the biggest gear ratio that I can get it in. Not quite the biggest. My rear derailleur up here is kind of messed up, so I can't actually get in my biggest gear. But this is my second biggest gear this bike could possibly be in. It's on the biggest ring in front here, and it's on a very small ring in the back there. Okay, so that's a very high gear ratio, which gives me a lot of resistance here. And so to produce this power that I'm producing right now about my crank, I'm doing it with a lot of torque, a lot of crank torque, and a relatively slow pedaling rate. Okay? I could produce that same power by shifting into a smaller gear. So I'm going to shift into my small gear on the front ring here. And then I'm going to shift into a bigger gear in the back here. Okay. And now you can see that there's a lot less resistance to my pedaling. This is a lot easier to do, so I don't have to produce as much torque about the crank, and I'm able to pedal it quite a bit faster. Okay? So less torque in this situation than when I was in that big old gear early on, but I'm able to cycle it at a faster rate because there's less resistance. Okay? So two different combinations of crank torque and pedaling rate that can be used to produce roughly the same power on the bike. Or I could use many different combinations within there, different gears between these two extremes, where I could then have, a more moderate amount of torque and a more moderate pedaling rate, again producing roughly the same power and roughly the same velocity of the bike, all other things considered equal. But just like in locomotion, where we tend not to see these widely varying stride lengths and stride frequencies to go at a certain speed, in pedaling, people tend to have a preferred pedaling rate, where if you put me on a bike that I need to produce a certain amount of power, I will pick my pedaling rate, and it'll tend to be somewhere in the range of like 90 RPMs. For most people that are reasonably fit, reasonably experienced cyclists, they'll tend to pick roughly 90 RPMs or so. Some might pick 80, some might pick 100, but roughly 90 revolutions per minute is a pretty normal, quote-unquote, preferred pedaling rate that a cyclist will pick to produce like an endurance-type power. Like for a fairly fit, fairly well-trained cyclist, this might be something in the range of like 200 to maybe 250, maybe 300 or so watts. 300 might be getting a little high for a lot of people, but typically in the range of like 200 something watts would be a reasonable power output for like an endurance type effort for a fairly fit cyclist. And people might pick a pedaling rate to produce that power in the range of 90 RPMs. They don't have to do that. They could produce that same crank power at 50 RPMs by shifting into a big gear. They could produce that same power at 130 RPMs by shifting into a smaller gear, but they tend not to do that. And at least in normal circumstances, they tend to produce a moderate amount of torque at a moderate pedaling rate of around 90 RPMs. So both of these studies were trying to get at the why of that choice of pedaling rate, which is kind of the theme of the class here that I'm hoping to establish. Rather than just observing that people pedal at 90 RPMs, let's see if we can figure out why people pedal at 90 RPMs. So two different approaches here to kind of get at that same question of what is it about this preferred pedaling rate that makes people want to pick it. The interesting motivational background here was early on in the introduction of the first reading, the Hagberg et al. Reading, where it's shown that if you throw people on a bike and measure their rate of oxygen consumption while they pedal at different rates on the bike, you might think that, well, maybe they pick the 90 RPMs because that's the most efficient pedaling rate, right? Like that's the rate of pedaling that for whatever power output requires the least rate of energy expenditure, the least oxygen consumption to pedal at that rate. That's not actually the case. That's not what people have been observing in previous studies before this one on pedaling rate. It seems to be observed that the most efficient pedaling rate is typically in the range of like 50 to 80 RPMs, where 80 is getting kind of close to 90, but 50 RPMs is a heck of a lot slower than 90 RPMs. This would be a very large difference. Like if you put me on a bike and say, pedal at 50, okay, now pedal at 90, that's a very, very large difference. Okay? So the pedaling rate that is most efficient in terms of the energy needed to produce a certain power on the crank is actually quite a bit below most people's normal quote-unquote preferred or subjective pedaling rate of 90 RPMs. So here they did an experiment where they had some fairly well-trained cyclists pedal on their own bikes on a treadmill at a roughly constant power output at different pedaling rates. So everybody pedaled at their own preferred pedaling rate that they use to produce power to go at 20 miles per hour. And then they also pedaled at two rates slower than preferred and at two rates faster than preferred. And again, between all of these, conditions here, they went to some effort to try and maintain the power output between them so that you're always producing the same power to go at that 20 miles per hour. Okay, it's probably not exact. That's really difficult to control exactly, but they did probably the best that they could here to make the power output at least very similar between the conditions. They then measured a host of variables from exercise physiology to see what, if anything, was like minimized at that preferred pedaling rate, or what is it about that pedaling rate that makes people want to pick it. If it's not efficiency or economy, what is it about that preferred pedaling rate that seems to be what's making people pick it? The results that they found are, and there's quite a few of them. The big take-home message is here in Table 3. This is where they show all of the variables that they measured, all of the outcome variables that they compared between the different pedaling rates. And here in the middle is showing the value of that variable when everybody pedaled on average at their whatever their preferred pedaling rate was. On the right is showing how much it increased or decreased when they pedaled at faster pedaling rates, and on the left is showing how much it increased or decreased when they pedaled at slower pedaling rates. Okay. These variables here, if you've taken a Kines 360 already, some of these will look familiar. If you haven't, you may not have heard of these things before. VO2 here is your rate of oxygen consumption while you're pedaling, so how much fuel you're having to bring in from the oxygen in the air to power your muscles. Generally, the higher this is, the harder you're working. So if this is lower, that means that it's an easier task for you. VE here is your rate of expiration. This is the rate at which you are expiring air from your mouth and from your body while you're exercising. And so this is also another thing that's generally the higher this is, the harder you're exercising. Heart rate here is also another index of kind of the intensity of the exercise. The faster your heart is beating, the more difficult the exercise is. PE here is perceived exertion, the individual's subjective report of how difficult it was, usually on a scale from like 1 to 20 or so. LA here is lactate accumulation, the concentration of lactic acid in the individual's blood. And again, the higher that is, generally the more difficult, the more intense the exercise is. And then these other variables here, just some other ones that they measured. I'm only going to talk about these ones on the top here. Generally, you can see here that for most of these variables, certainly if you increased your pedaling frequency, if you were asked to pedal at a rate faster than your preferred pedaling rate, then all of these variables increased, and they typically increased by quite a bit. Heart rate really only went up by about 5 beats per minute, but when you're already working at 180 beats per minute, which is pretty fast, an additional 5 is quite a bit. But just generally speaking, pedaling at the faster rates led to pretty large increases in all of these exercise physiology related metrics of effort compared to pedaling at your preferred pedaling frequency, which again for these participants was on average about 90 RPMs. If they pedaled at slower frequencies, again, things on average tended to increase. You tended to use more oxygen or inhale more oxygen into your body to power your muscles. You tended to increase your rate of expiration of air from the body. You tended to increase your heart rate, your perceived exertion, your lactate, etc. But notice here that these are not terribly large increases, right? Heart rate when I pedaled at the slower frequencies went up by like 1.5 beats on average, compared to 5 beats on average at the faster rates. VO2, rate of oxygen consumption, went up by 3.5 liters per minute compared to 11.3 liters per minute when I pedaled at the faster frequencies. Okay, same thing for basically all of these variables here. Yes, they were typically minimized or typically lowest at the preferred pedaling frequency, but they tended to really go sky high when I pedaled at the faster unpreferred pedaling rates compared to when I pedaled at the slower unpreferred pedaling rates. So this is what they base the conclusion on, that there's an advantage in cycling at these preferred pedaling rates. They rationalized this in comparison to earlier studies showing that like VO2 was minimized at slower pedaling rates by saying that this was a different population. These were well-trained, experienced cyclists compared to the earlier studies being on people that weren't cyclists, just people that were given a bike to ride in the study. And also that this was done on using actual bikes on a treadmill, while as in the earlier studies it was usually on like a stationary bike, which is a little bit different from an actual like outdoor bicycle. If you dig into the actual results of the data here, it looks a little bit like most of their variables were also minimized at slightly slower pedaling rates, like pedaling rates in the range of like 60 to 70 to 80 RPMs rather than the preferred rate of 90 RPMs. So in each of the figures that they have shown in the paper here, on the x-axis is the percent difference from preferred. So if it's to the left of 0 here on the x-axis, that means slower than the preferred pedaling rate. And if it's to the right, that means higher than the preferred pedaling rate. On the y-axis here is the percent of the response, or the percent of that variable that they're examining in the figure relative to its value at the preferred pedaling rate. Okay? So if it's above 100 here, that means it's higher than the value at the preferred rate, and if it's below here, that means it's below the value at the preferred rate. Okay? So in this one, for example, this is showing the VO2, the rate of oxygen consumption. The dotted line here, the net VO2, and any time on any of these figures you see like a variable indicated as a net variable, that was where they subtracted out the value of that variable in what they called unloaded cycling, where they like took the chain off the bike and just had you cycle your legs without the resistance of the bike at whatever pedaling frequency you were working with there. So that one's kind of giving you an idea of like what was the extra cost here in terms of VO2 or in terms of whatever variable, purely related to the extra resistance on the bike and not related to like using your muscles to cycle the legs faster and faster. I don't really know necessarily what's the motivation for the net variables. I guess it's really just isolating the effect of resistance, but for like overall performance, it's going to be the combination of both of these things, cycling the legs faster and the extra resistance. So I was focusing here on the solid line, the actual VO2, not the net VO2, the value where the VO2 due to cycling the legs at faster rates was taken out here. So if we look at their actual VO2, at least on average, that was minimized at a pedaling rate that was I'd say 15 to 20% below the preferred pedaling rate, which is pretty similar to what you see in other studies, where the most economical pedaling rate, the one with the lowest VO2 to produce a certain amount of power, is a little bit slower than the preferred pedaling rate. However, if you look at some of these other graphs, like here is showing my rate of expiration, the rate at which I'm expiring air from my body. You can see here, at least for the gross one, not for the net one, that was minimized at just about 10% below the preferred pedaling rate. And if I look here at blood lactate, which is this solid line there, that one's also minimized at 10 to maybe 15 to 20% below the preferred pedaling rate. So, general story here seems to be pretty consistent with the earlier findings that your preferred pedaling rate is not necessarily one that minimizes our classical exercise physiology related indices of the difficulty or the challenge of the exercise. Okay? We could pedal at slightly slower rates, slower than this 90 RPMs that everybody seems to like, or roughly 90 RPMs that everybody seems to like, and possibly reduce our lactate accumulation, or possibly reduce our rate of expiration, or possibly reduce our oxygen cost of performing the motion. What they do suggest here is that notice that these differences are fairly small. Like if I compare my VO2 here at my preferred pedaling rate, which is right about there, maybe 105% or so of the minimum, compared to my VO2 at the minimum here, which was 20% slower, that's a pretty trivial difference, maybe a few percentage points. So suggesting that I could decrease my pedaling rate a lot, and it's not really going to affect my VO2 much. If I increase my pedaling rate, then things start to get kind of sky high. And that's generally, not always the story, but that's generally the story with a lot of the results here. Like if I look at lactate, if I compare like 0 to minus 20, not a huge difference. If I compare 0 to plus 20, then that's where I start to see a really big difference in like extra accumulation of lactate. So kind of take-home message here is that the preferred pedaling rate, if you're not sure what your preferred pedaling rate is, if you want to be on the safe side in terms of minimizing physiological effort, maybe pedaling a little slower than what naturally feels normal and comfortable might be the way to go. So increase your torque a little bit and decrease your pedaling rate. Going in the other direction, decreasing your torque and pedaling at a faster rate than what feels comfortable, that probably is going to be extra physiological effort based on the findings of this one. But here, still again, not really a clear answer to the question of why we prefer to pedal at that rate. It looks like on average we might be able to minimize or possibly reduce things like VO2 or things like lactate accumulation by pedaling at rates that are slightly slower than our preferred pedaling rate. This is where study number 4 in pedaling and endurance cycling comes in. Here, they were using a musculoskeletal model of the body to generate computer simulations of pedaling. So they had individuals, fairly well-trained cyclists, again, pedal on a bicycle in a lab at 3 different pedaling rates, at 75 RPMs, at 90 RPMs, so the typical preferred pedaling rate, and 105 RPMs, in all 3 cases at a constant power output of 265 watts. A pretty, I'd say that's a little high for the average person, but for a well-trained endurance cyclist, this is one that they could probably hold for a pretty long amount of time as for an endurance effort. From those computer simulations that they then generated of these individual human subjects pedaling bikes at these rates, they were then able to extract from the simulations information that is not accessible from like a live human. So things related to the activation levels of the individual muscles in the leg, the amount of force and amount of stress of the individual muscles in the leg, and various other things that you're not able to identify easily or at all in experiments on human subjects. They then compared what was different in terms of those muscle level kind of costs or efforts between the 75 RPMs, the 90 RPMs, and the 105 RPMs. Take-home message here is down on figure 1, I believe, okay, where here on the x-axis is all the different quantities of like cost and effort at the muscular level that they calculated from the simulations of the different pedaling rates in the study. The gray box in all, how many did they have here? I think they had 9 or so. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9 different definitions of like the muscular cost of the movement here. The gray box is, in all of them, in all 9, is pedaling at the 75 RPMs. The black box is pedaling at the 90 RPMs, so the one that's typically closest to the preferred pedaling rate that people just naturally choose. And the white box is the 105 RPMs. So you can see here that for each of these kind of muscle level definitions of effort, the black box, the 90 RPMs, is always the smallest one. Okay, it's always lower than the same quantity from the 75 RPM simulation and the same quantity from the 105 RPM simulation. Okay. These different quantities here, average activation is like the average activation level of all the muscles in the simulation. Integrated activation is that same thing, taking those averages, but then also scaling them by time, with the idea that the rate of pedaling is the time of the pedaling cycle is changing here. Peak activation is basically adding up all the peak muscle activations of all the muscles. Same deal here for the muscle forces, the average force they were producing, the peak force they were producing. If you divide the muscle force by the size of the muscle in terms of its cross-sectional area, you get the stress on the muscle. So again here, the average stress of the muscle versus the peak stress. If you take that stress and raise it to the power of 2, then that's considered an index of endurance in activities like this. And so there you can get the average endurance level of the muscles, or the peak challenge to the endurance of the muscles. And so notice here, by all of those muscle level definitions that they determined from these simulations, the black box is always the smallest. And in some cases, it was dramatically smaller than the other result at the other pedaling layers. Like here for the integrated activation of the muscles, the activation level of the muscles integrated over the pedaling cycle time was dramatically smaller here by a factor of like 2 to 3 times at the 90 RPMs compared to the 75 or the 105 RPMs. And then also here, and perhaps more important for like long distance endurance type cycling, their index of endurance of the muscles, like how long you would mechanically be able to sustain that effort level of those particular muscles, was dramatically lower by a factor of like 2 almost for the endurance related indices here of the muscles. Okay. So suggesting here, in combination with the results of the previous study, that maybe it's not necessarily the rate of energy expenditure, the rate of oxygen consumption, or the rate of lactate accumulation, the typical indices of like the difficulty or the intensity of exercise and exercise physiology that explains the pedaling rate here in cycling. Maybe it's these more muscle level, more mechanical type variables, where the preferred pedaling rate minimizes how active my muscles have to be, or minimizes the stress on the muscles such that my endurance of the muscles is activated, or is minimized, that I can keep going at that pedaling rate and at that level of intensity and speed and work for the longest amount of time possible. Okay, that is it for today, and we will see you next time.